Okay, so for this problem, we have Jeremy and George walking in town. Jeremy's walking east on Main Street at 40 feet per second. Hey, that's a rate, so we know that's going to be a derivative. Meanwhile, George is going south on Byron Avenue at a rate of 30 feet per second. That's another rate. That's going to be another derivative. Cool. So we have Jeremy wishes if I can talk here, determine when their straight line distance in between them, if it's increasing or decreasing when he is 400 feet from the corner and George is 500 feet from the corner. So on our picture over here, we have Jeremy going to the right. We know his rate. Now, the distance from the corner, because he's walking away, we know that's changing, so that's going to be a variable. We have George walking south with his rate, so he's getting closer to the corner, so we know that that's going to be changing. And we know the distance in between them is going to be changing. So, as we look here, we know x is going to be 400 feet and y is going to be 500 feet. If we wanted, we could go ahead and figure out what z is by using the Pythagorean theorem. Also, we have the rate of Jeremy. Since the distance is getting bigger, we know that that's going to be positive. We also have the distance for George. That rate, he's walking towards the corner, so that distance is getting shorter, so that's going to be a negative rate. And we're wondering about the rate in between them. So we're looking at the rate of z is what we're wondering about. So we're wondering about dz over dt. So we're going to find an equation, the Pythagorean theorem, that relates our three variables. Now to get our rates to show up, we just have to do our derivative. Exponent in front, decrease it by 1, times the derivative of the inside, derivative of x with respect to t, plus exponent in front, decrease it by 1, times the chain rule, derivative of the inside, derivative of y with respect to t, equals exponent in front, decrease it by 1, chain rule, derivative of the inside with respect to t. Well, we could just go ahead and divide everything by 2 to simplify it a little bit. Then all we have to do is start throwing stuff in. We know x is 400. We know dx dt is our 40. We know our y is our 500. We know our dy dt right here is negative 30. And we know our z ends up being this. We can throw that in. Now we could simplify that a little bit. I just didn't. And that's got to then have our dz dt, what we're looking for, hanging out by it. So all we have to do is go ahead and simplify this down. So we can get 1600 here minus 1500 is 100 divided by the square root of this, which that ends up being 10 root 42. So if on the left-hand side you had 100, the right-hand side you had 10 root 41 times your dz over dt, that's where we get this from. First of all, we don't like roots in the bottom, so we'd have to simplify that down. So we get 10 root 41 over 41, and that would be our dz dt. Units-wise, that would be feet per second. Now, more than likely, he's a math guy. He might like this number, but it might be nice to also have a decimal approximation. So to really answer the question, we would say it's increasing at a rate of about 1.56 feet per second, or increasing at a rate of 10 root 41 over 41 feet per second for an exact answer. If in doubt, put the exact answer down and the decimal approximation. If you have both, you'll be covered either way. So one last problem here. We have the inside of an engine. We have a 7-inch connecting rod which connects our piston to here. We have a 3-inch radius on our cranking shaft. It's rotating at 200 revolutions a minute, which is a relatively slow revolutions per minute when you think of what normal engines are in your car. We're wondering, what is the velocity of the piston at the angle of pi over 3? So we know our angle is pi over 3, and you know that's radians. Now, if we look at this triangle here and kind of just look at the triangle and ignore everything else, we would get this. The, the piston comes back down, so this distance here changes. The connecting rod doesn't change, that's always the same. The crankcase radius is always the same, so this is this crankcase right here. This is our connecting rod right here. They're always the same. What changes is how far the distance between the center of the crankshaft and the piston is, which is x, and this angle. Those are the things that change. We're wondering about the velocity of the piston. That would be the speed of the piston. So we're wondering about dx over dt. Because x is our distance, we're looking at a speed, the velocity, so we know that's a derivative. Well, we have a theta, and we are given that our going clockwise at 200 revolutions per minute. That's really the rate of change of our angle with respect to time. However, we got to adjust this a little bit. Right now we have 200 revolutions per minute. We need to be dealing with radians per minute. So you got to think, oh, well, it's 2 pi radians for each one revolution. So we have revolutions at top, revolutions in the bottom. Revolutions are going to top, leaving us with radians per minute. So we take the 2 pi times our 200, and we get 400 pi radians per minute. So what's going to relate all this? Well, it's underneath. It's the law of cosines. Going back to geometry, algebra 2, and also pre-calc. So we have our law of cosines. The side opposite your angle squared is equal to adjacent side to your angle squared plus other adjacent side to your angle squared minus 2 times your 2 adjacents, cosine of your angle in between the adjacents. Well, to get all these rates to show up, we just have to do our derivative. Well, derivative of 7 squared is 0. Derivative of 9, you know, is 0. Derivative of 2x, put the 2 in front, decrease it by 1. Chain rule, derivative of the inside, derivative of x with respect to t, minus, oh, we're going to have a 6 here, but oh, we have a 6x times a cosine. We're multiplying variables. Oh, cool. We get to do product rule. So negative 6, derivative of the first, dx dt, times the second. Oh, I guess I flipped the order, but you can add in any order you want. You can think derivative of the x with respect to t, derivative of the first times the second, plus the first, which is your x, derivative of the second is cosine. Derivative of cosine is that negative sign that shows up here, times the chain rule, derivative of the inside, derivative of theta with respect to t. Okay, so now we need to go ahead and try to get, we're trying to solve it for dx dt. So let's go ahead and try to get dx dt by itself. So we could go ahead and distribute through, get all the dx dt's on one side, get the non-dx dt's on the other side. So we could take this to the other side, distribute through, would be a plus 6x sine theta dx, or d theta dt, so we have that here, distribute through your negative 6, it'd be a negative 6 cosine theta dx dt, so we add that to the other side, that's why it's positive. We pulled out the dx over dt here. To get dx over dt by itself, we have to divide by the parentheses. So we get the right side divided by the parentheses. So now we can maybe try to answer the question. We know our d theta dt. We know theta, but we don't know x. But we can figure out x. Remember, theta is pi over 3, so we could use law of cosines again with pi over 3 in here to help us find x. So we get 49, 9, x squared minus 6x, and then you got to think cosine pi over 3. Oh, that's just 1/2. So this is just really minus 3x here, so now this is just a nice normal quadratic. So we'd have our x squared minus our 3x. We'd have to subtract the 49 from both sides, giving us this. Now this one does factor quite nicely. We get two answers of -5 and of 8. So we know in the context of our problem our x can't be -5, so we know it's 8. So we take our derivative, which I copied down over here on the right. We throw in our x being 8. We throw in our angle being pi over 3. We throw in our d theta dt being 400 pi. So if we plug all that stuff in here, we would get this. Then all we have to do is simplify it down. We get this here, which is approximately -400 or 4,018 inches per minute. Now, technically speaking, the exact answer would be what we have here, and that would be inches per minute. Now, maybe you're wondering once again, how do we know that we're dealing with inches? Well, it's got to be the units of the top, units of x. Looking up here, all of our lengths were given to us in inches. And the units of the bottom have to be the units of this. Units of any of our time was always related to minutes.